Welcome to Brain Vision.
Okay, so in this question, we're dealing with the biggest pipe of a pipe organ, and we're told that the length of this pipe, L, is 4.88 meters. And in part A, we're supposed to find its fundamental frequency when it is closed at one end, and in part B, we're supposed to do the same thing when it is open at both ends. And for part A and B, the temperature in Celsius is 0 degrees, which is a little bit different from what we normally do, because most of the time when we're dealing with speed of sound, um, we're dealing with room temperature. So that's why we can assume that the speed of sound is 343 meters per second. Um, so since the temperature is something different, we have to figure out what our new speed of sound is for this for this different temperature. So to do that, we need a formula for relating the temperature of the air to the speed of sound. And there is one, which is that the speed of sound, v, is equal to 331 times the square root of 1 plus the temperature in degrees Celsius, Tc, divided by 273. So if we take a look at this, we can see that v at 0 degrees Celsius is going to well, we plug in 0 for Tc under the square root, so 0 divided by 273 is 0. 1 plus 0 under the square root is 1. The square root of 1 is 1, so 331 times 1 is just 331. So we'll say V0 is 331 meters per second. So now we can get going with what we normally do for these kinds of problems. So in part A, we are dealing with what the fundamental frequency is if the pipe is closed at one end. So for that, I'll draw just a quick little diagram. So we have the pipe organ closed at one end and then open at the other. So at the closed end, we need to have a node for the standing wave, and at the open end, we need to have an antinode, which means that the fundamental frequency, the smallest number of nodes and antinodes that you can fit into this length of tubing, would be you have a node at the left side and they have an antinode at the right side, which, if you take a quick look at that, that is 1/4 of the total wavelength. If you imagine it continuing, you'd see that it'd have to return back to a node that would be half a wavelength and then go back to the opposite antinode and then come back to the node to complete a full wavelength. So our length of the tube, L, is equal to lambda divided by 4, which we can rewrite as 4L is equal to lambda. Then, now we have a way that we can get to finding our fundamental frequency. So, F, the fundamental frequency, will be equal to V, the speed of the wave, in this case V0, divided by lambda. And so we just said that 4L is equal to lambda, so we can rewrite this as V0 divided by 4L. And we have values for V0 and we have values for L, so we can go ahead and just plug in everything. So our expression for the fundamental frequency is then 331 meters per second divided by 4 times 4.88 meters. And if you plug this into your calculator, you will get that the fundamental frequency is 17.0 hertz. And that's our answer for part A. And then for part B, we do a very similar thing. Switch colors just to differentiate. So now the pipe is open at both ends. So if we redraw our diagram, like how we had in part A, so here's our length of tube, but now it's open at both ends. So at each end, there has to be an antinode. So in order to get the fundamental frequency, we want as few antinodes and nodes in the length of tubing as possible. So the way to do that is you start at an antinode at one end, and then you go to a node in the middle, and then you go to the opposite node at the other end. And if you look at this, you'll see that this is half the wavelength or half the full wavelength. If you continue this, you'll see to get a full wavelength, you'd have to go back to a node and then back to the antinode that we have at the left side if you're extending the wave to the right. So we can see that the length of the tube, L, is 1/2 the wavelength, or lambda over 2, which we can then rewrite as 2L equals lambda. And then we just do the calculations like we did before. We still have that the temperature is 0 degrees Celsius. So we'll use V0 one more time, or V0. So in this case, the fundamental frequency F is equal to V0 over lambda. But now lambda is equal to 2L. So V0 divided by 2L is equal to F. And then we plug in our numbers. 331 divided by 2 times 4.88. And if you plug that into your calculator, you will get that the answer for part B is 33.9 hertz. All right. And that makes sense because the only difference between part A and part B was that we have a 2 into the denominator instead of a 4. So 17.0 times 2 is 34. There's a rounding difference between the two answers, so it's fine that it's off by 0.1 hertz. But part B is roughly double to the answer for part B is roughly double to the answer to part A, which makes sense from our formulas. All right, so in part C, we just redo the calculations from part A and B, but now we are doing it for what if the temperature is 20 degrees Celsius. So now in part C, Tc is 20.0 degrees Celsius. So now we have a new speed of sound, so we have to recalculate V. So if we go ahead and plug in 20 for the formula that we had for V before, get that V is equal to 331 times the square root of 1 plus 20.0 over 273. And if you plug that into your calculator, you'll get that V, the speed of sound at 20 degrees Celsius, is 343 meters per second. Which, if you think about it, 20 degrees Celsius is about room temperature. So it makes sense that, we end up with our normal value for the speed of sound when we use 20 degrees Celsius in this formula. So we're dealing with, our V for part C is going to be 343 meters per second. And then we just redo the calculations from both part A and part B using 343 meters per second for our V instead of 331. So for the closed tube, I'll write this in the black pen like we did before. We just use the same formula as before. So F is equal to V divided by lambda. But lambda is equal to 4L, so it's V over 4L. And when we plug in our numbers, we get 343 divided by 4 times 4.88. And if you put that into your calculator, you'll get that the fundamental frequency is then 17.6, 6 hertz. And so that's one answer. And then we'll do it for the open tube as well. And I'll do this in blue to match what we did in part B. So now F is equal to V over lambda, but lambda is 2L. So we have V over 2L. And then we plug in our numbers. V is 343 meters per second. And then we have 2 times 4.88. And you plug that into your calculator and you'll get that the fundamental frequency in this situation is 35.1 hertz. And there you go.